In this video, we're going to cover properties of the equilibrium constant. We're going to talk about ways that you need to manipulate your equilibrium constant depending on how you're manipulating your equation or what's going on with a reaction. So let's start by reversing a reaction. If you reverse a reaction, so if you flip the products and reactants, our equilibrium constant is inverted, or you'll take your equilibrium constant and you will go 1 over your equilibrium constant like so. So if our equilibrium constant was 100, I would do 1 over 100 and I would end up with 0.01. So again, reversing a reaction, we invert our equilibrium constant. Next, if we multiply our reaction by a factor, we are going to raise it to a power of whatever that factor is. So in our example equation here, a plus 2b will give us c with an equilibrium constant of 100. If I multiplied every item or every species in our reaction by a factor of 2, then I would raise my equilibrium constant by a factor of 2. So if my equilibrium constant was 100, I would raise it to a power of 2. 100 to the second power would give us 10,000 as our new equilibrium constant if we're multiplying it by 2. Okay, finally, if we add reactions together, we are going to multiply their equilibrium constants together. So I have two reactions here. Equilibrium constant 1 is 100, number 2 is 5. Our overall reaction, and again, we've crossed out any spectators that exist in our reactions. So I have C on both sides. That's going to be eliminated. And then also, nope, that's it. We just add them up. So I'm going to multiply my two numbers. So the equilibrium constant from reaction number 1 was 100. From reaction 2, it was 5. 100 times 5 is 500. Okay, so when we add them together, we multiply their values like so. All right, so let's go through some examples. So we have this reaction, and I have 3 variations of that reaction. Now let's see what happened. So in our first reaction, we basically just flipped it. So we took our original reaction and reversed the directions. So our original equilibrium constant was 4.2 times 10 to the negative 2. So I would just do 1 over that. So 4.2 times 10 to the negative 2. And if I plug that into my calculator, I will end up with 23.8. Okay, and remember, our k does not have any units. All right, in equation 2, we've multiplied everything by a factor of 3. So since we multiplied everything by a factor of 3, we are going to take our equilibrium constant and we are going to raise it to a power of 3. So I have 4.2 times 10 to the negative 2. I'm going to raise that to a power of 3 since I multiplied everything by 3. And my new equilibrium constant will be 7.4 times 10 to the negative 5. Okay, this last one's tricky. So it's not only been reversed because we're starting with z and w, so we did reverse it, but we've also multiplied everything by a factor of 2. So we have to do 2 things here. So we are going to do 1 over our equilibrium constant, which is 4.2 times 10 to the negative 2. But then I am also going to take my equilibrium constant, and since I multiplied everything by a factor of 2, I'm going to raise it to a power of 2. Okay, so when I do that, I get 566.4. Okay, so you can do more than one thing to your equation, requiring you to do more than one thing to your equilibrium constant. All right, let's look at our next example. It says, how were equations 1 and 2 manipulated to create equation 3? Well, let's take a look. So here, it looks like we just added them. So A and B are spectator ions. Those are going to cancel out, as are A's. So we just added those together to get those. Also, remember when we add our reactions together, we're going to multiply our K values. So 4 times 3 gives us 12 down here. Okay, here's another example. In this third example, it says find Kp, and it gives us a new reaction. All right, in our second example, we have two reactions, and it says to find Kp. Well, it looks like our second reaction has been reversed, and I know that because CO2 is on the left side here, but it's originally on the right side. So I'm going to go ahead and rewrite my second equation. So I have CO2, and then I have nickel, and then I have NiO, and CO, carbon monoxide. Okay, so I don't get confused, let's go ahead and cross this one off because I reversed it. Okay, let's cross out our spectator ions. So it looks like our NiO goes away, and so does our nickel. And then when I add these up, I'm just left with my final reaction here. So because I added them together, I'm going to multiply those two values. So 50 times 700. Oh, wait a second. We reversed our second equation, so it's going to be 1 over 700. So 50 times 1 over 700. And I will get a value of 0.0714 as our new value for our equilibrium constant. All right, let's look at our final example here. We have two reactions, and it says find K for the overall reaction. So let's see. Do we need to reverse anything? Well, it doesn't look like it. It looks like everything's on the right side. So did we add them together? Let's cross out some spectators and see what goes away here. So it looks like our AnH2 will cancel out. That exists on both sides. And then I believe that is it. So we're going to have one A+3 ion. We have two of these NH2s. And then on the right side, we have one of this NH2, 2, and that's it. Okay, so we just added these together. Since we added them together, we're going to multiply our values. So 200 times 125 gives us 25,000 as our value. And that's it. That's all there is to it.